There is a rock on the ground in front of you. You can see it. You can reach down and pick it up. Feel its weight in your palm, the roughness of its surface, the cold solidity of it pressing against your skin. If you drop it, it falls. If you throw it, it arcs through the air along a single traceable path and lands exactly where physics tells you it will. The rock is there. The rock is real. The rock follows rules you can understand, predict, and trust. Now forget the rock, because everything you just felt, the weight, the solidity, the certainty, is not a property of the universe. It is a property of your nervous system. It is the story your brain tells you because your brain evolved to navigate a world of medium-sized objects moving at medium speeds through a medium amount of space. Your intuition was calibrated for rocks, not for reality. And the moment you descend below the surface of that rock, below the molecules, below the atoms, below the protons and neutrons, into the actual architecture of what things are made of, you do not find smaller rocks. You do not find anything your mind was built to understand. You find something so profoundly, structurally different from ordinary experience that one of the greatest physicists who ever lived said, without irony and without exaggeration, that nobody truly understands it. That physicist was Richard Feynman. And what Feynman discovered, what he formulated into one of the most elegant and disturbing mathematical frameworks in the history of human thought, is that the universe, at its most fundamental level, does not work the way anything works. Not the way machines work, not the way weather works, not the way thought works. The universe, at the level where all things are ultimately made, operates by a principle that has no analog in daily experience, no intuitive entry point, no comfortable metaphor that captures it without betraying it. Every analogy you reach for will be wrong in some important way. And the most honest thing that can be said about it is also the most unsettling. A particle moving from one place to another does not take a path. It takes every path, all of them, simultaneously. Not as a metaphor for uncertainty, as a literal, measurable, experimentally verified description of what actually happens. You are made of particles that have been doing this since before the Earth existed. Stop and let that settle. If this is the kind of question that keeps you awake, if this is the kind of discovery that makes you feel the ground shift slightly beneath your feet, then stay here. Leave a like, subscribe to the channel, and don't look away. What comes next does not get easier. It gets deeper. The story of how Feynman arrived at this is not a story of gradual accumulation. It is not the story of a scientist slowly building a tower of knowledge, brick by careful brick. It is the story of someone who looked at the foundations of physics and realized the bricks themselves were made of something no one had named yet. Feynman was 23 years old, a graduate student at Princeton, when he began working on what would eventually become his doctoral dissertation, a new way of formulating quantum mechanics, one that bypassed the abstract algebraic machinery of the prevailing approaches and replaced it with something almost hallucinatory in its directness. Instead of calculating what a particle does by solving differential equations about its state at each moment in time, Feynman asked a different question entirely. He asked, what if you added up everything? What if, instead of asking which path a particle takes, you assumed that it takes all of them, and then you summed their contributions, accounting for how each path interferes with every other path, and you let the mathematics tell you what emerges from that infinite sum? What you get when the calculation is done is the same result you would measure in a laboratory. The interference between all those phantom paths, the cancellation of some, the reinforcement of others, produces, with perfect precision, the probabilities you observe when you actually measure where a particle goes. This is called the path integral formulation of quantum mechanics, or, in language that reveals more of its strangeness, the sum over histories. The name matters, because what Feynman was saying is not just that particles are uncertain. Uncertainty was already in quantum mechanics before Feynman. What he was saying is something more radical, that the history of a particle, its trajectory, its past, the record of where it has been, is not a single line connecting two points in space-time. It is an infinite superposition of every line that could have connected those points. The particle you detect at a specific location carries within its arrival the ghost of every other place it could have been. The present moment contains the uncollapsed weight of all possible pasts. And this is not a philosophical interpretation layered on top of the math. This is the math itself. This is the mechanism. This is what the equations say when you take them seriously and follow them without flinching. The consequences, once you begin to trace them, do not stay small. They do not stay safely confined to laboratories and particle accelerators and the nanoscale machinery of atoms. They reach up. They extend outward. They touch the formation of stars, the structure of galaxies, the behavior of light crossing billions of light-years of empty space. The photons arriving at the James Webb Space Telescope from galaxies that existed when the universe was only a few 100 million years old. Those photons traveled to us by taking every possible path through the cosmos. They curved around gravitational fields. They interfered with their own trajectories across distances too vast to visualize. And when the detector registered them, when the measurement was made, all those possible histories collapsed into a single signal. A point of light in a photograph that people on Earth looked at and felt small. You are made of atoms. Your atoms are governed by quantum mechanics. Your quantum mechanics is, in its deepest formulation, a sum over all possible histories of every particle that constitutes you, which means that, in some mathematically precise and philosophically vertiginous sense, you are the result of a sum that was never finished, a convergence of infinite possibility into the temporary, improbable, specific thing that is reading these words right now. The rock on the ground feels solid, but the solidity is approximate. It is statistical. It is the emergent behavior of an almost incomprehensible number of particles, each of which, individually, has no fixed position until it interacts with something else. The rock does not sit on the ground the way you imagine it does. It hovers, in a quantum mechanical sense, in a superposition of positions so tightly clustered around a single point that for all practical purposes, for all human-scale purposes, it might as well be fixed. The rock is solid the way the surface of the ocean is solid if you are moving slowly enough and carefully enough that you never fall through. Get fast enough, small enough, precise enough, and the surface gives way. Below the surface of everything is a place where the rules you know do not apply. Feynman spent his life in that place. He was not afraid of it. He was delighted by it, in the way that certain kinds of minds are delighted by the discovery that reality is stranger than imagination. Not as a failure of imagination, but as an invitation. He famously told students and colleagues, and anyone who would listen, that the first step to understanding quantum mechanics is to accept that you will not understand it in the way you understand other things. There is no deeper classical reality underneath that makes it make sense. There is no hidden mechanism that, once revealed, will make particles suddenly seem familiar again. The strangeness is not a symptom of incomplete knowledge. The strangeness is the knowledge. And it goes further than you think. Because what Feynman built, with the path integral, was not just a tool for calculating particle behavior, he built a lens. A lens that, when pointed at the largest and most extreme structures in the universe, at black holes, at the fabric of space-time itself, at the first instance of the cosmos, reveals a silence at the center of physics that no one has yet been able to fill. A silence where the two greatest theories of the physical world should speak together, and instead say nothing at all. The ground you are standing on is about to give way. You need a reference point, something human, something you can hold. Close your eyes for a moment and imagine a single hair from your head. Not a strand, just one. Now imagine slicing that hair lengthwise into 10 equal slices. Take one of those slices and slice it again. Then again. Keep dividing, methodically and patiently, until you have divided that original width 100,000 times. The fragment you are left with is approximately the diameter of a hydrogen atom, the simplest atom in existence, the most abundant element in the universe, the building block of stars and the majority of all ordinary matter that has ever existed. It is so small that if you placed a single hydrogen atom on the period at the end of this sentence, you would need to fit approximately 1 million of them side by side just to span that dot. Now go smaller. The nucleus of that hydrogen atom, the single proton sitting at its center, is 100,000 times smaller than the atom itself. If you scaled the atom up to the size of a football stadium, the nucleus would be a grain of sand on the 50-yard line. And below that nucleus, inside the proton, there are quarks, particles bound together by the strongest force in the known universe, the strong nuclear force, which is so powerful that it has never once, in the history of experimental physics, allowed a single quark to exist in isolation. Quarks are confined. They are always bound to other quarks. They have never been observed free. And it is here, at this scale, in this territory, so deep inside matter that no human instrument has ever directly seen it, only inferred it, that Feynman's sum over histories operates. This is where the path integral lives. This is the arena where every particle travels every possible path, where reality is not determined but probabilistic, where the trajectory of a thing is not a fact, but a superposition of facts, and where the act of measurement, of interaction, of observation in any physical sense, is the mechanism by which possibility becomes actuality. Let that land before continuing. You are not dealing with the strange behavior of exotic particles in extreme conditions. You are dealing with the foundation of everything that exists. The electrons in the atoms of your hand are, right now, obeying the same quantum mechanical rules that Feynman formalized. They are not at fixed positions. They exist in probability clouds, wave functions, that describe not where they are, but where they might be found if you looked. The chemical bonds that hold your molecules together, that give your cells their structure, that enable your neurons to fire, and your muscles to contract, and your heart to beat, depend on quantum mechanical effects that have no classical explanation. Without the uncertainty principle, without superposition, without the interference of probability amplitudes, atoms would not form stable structures. Matter as you know it could not exist. The solid world is built on a foundation that has no solidity. Now take this picture and let it breathe outward for a moment. Not deeper, outward. Because the same formalism that governs the behavior of quarks inside a proton also governs the behavior of photons, particles of light, as they travel across the cosmos. And here, the path integral reveals something almost unbearably beautiful and equally disturbing. When a photon is emitted from a distant star and travels toward Earth, it does not travel in a straight line in the way that a thrown ball travels in an arc. It travels along every possible path simultaneously. It curves around gravitational fields. It takes routes that seem absurd, routes that go in the wrong direction, routes that double back, routes that would take millions of years longer than the most direct line. All of those paths contribute, in varying degrees, to the probability of where the photon arrives. Most of the contributions from extreme detours cancel out through destructive interference. They subtract each other, mathematically, so their net effect is near zero. The paths closest to the classical straight-line trajectory reinforce each other through constructive interference and dominate the final outcome. This is why, in your ordinary experience, light appears to travel in straight lines. Not because it does, but because the interference pattern produced by all those simultaneous paths converges, for large-scale objects and large-scale distances, into behavior that approximates classical physics. The straight line is not the truth. It is the average. It is the peak of a probability distribution that contains, beneath its surface, an entire uncountable ocean of phantom trajectories. This phenomenon, the way classical behavior emerges from quantum mechanics through the cancellation of extreme possibilities, has a name: the correspondence principle. At large scales, quantum mechanics becomes classical mechanics. The strange dissolves into the familiar. The ocean calms into a surface, and the surface looks solid enough to build a world on. But the ocean is always there, beneath every surface, and it is never truly still. Feynman understood this better than anyone, and it made him suspicious of intuition in a particular way. Not as a faculty to be discarded, but as a tool to be used with full awareness of its limitations. He was famously direct about the danger of demanding that physics make sense in the way human experience makes sense. He would tell students that the electron does not behave like a wave, and it does not behave like a particle, and it does not behave like a tiny billiard ball, and it does not behave like anything you have ever seen before. And every model you construct using familiar objects will be wrong in some important way. The question is not whether your model is right. The question is whether it is useful, and in what regime. The path integral formulation is useful, extraordinarily, almost terrifyingly useful. It underlies the most precisely tested theory in the history of physics, quantum electrodynamics, or QED, the quantum theory of how light and matter interact. QED predicts the magnetic moment of the electron, a specific numerical value that can be measured in the laboratory, with an accuracy that, if it were a measurement of the distance between New York and Los Angeles, would be correct to within the width of a human hair. No theory in any field of knowledge has ever made predictions that accurate. The agreement between theory and experiment is not approximate. It is not close. It is one of the most extraordinary intellectual achievements in human history, and the engine beneath that achievement is the sum over histories. The idea that you add up all the ways something could happen, weight each by its probability amplitude, let the interference pattern emerge from the sum, and read off the result. The universe, at its most fundamental level, is a computation over all possible versions of itself. And the answer, the observable world, is what survives when all the alternatives have destroyed each other. Think about what that implies. Every time a photon hits your eye and triggers a visual signal, every act of seeing, every interaction between light and matter that has ever occurred since the first stars ignited, that event has been the result of an infinite sum, a superposition of every path that photon could have taken, every way that interaction could have unfolded, every possibility that did not happen, but that nevertheless shaped, through its participation in the calculation, the possibility that did. The universe is continuously summing itself. Reality is, moment by moment, the residue of a computation that includes everything that did not become real. You are a residue. and so is every star you have ever looked at. But here is where the ground truly begins to tilt. Because if every observable event is the result of an interference pattern between possibilities, then the question of what counts as an observation, what counts as a measurement, as an interaction that collapses the wave function, is not a technical question with an obvious answer. It is a question that strikes at the heart of what reality is and who or what gets to define it. Feynman, when asked this question, would often redirect. He would say, calculate. The formalism tells you what to predict, and the predictions agree with experiment. Do not ask what it means. The meaning, he implied, might be outside the reach of language, built for a world of rocks and trees and medium-sized certainties. But the meaning does not go away just because it is uncomfortable. The meaning accumulates, quietly, at the edge of the calculation. And somewhere at that edge, somewhere between the precision of QED and the disturbing silence at the center of a black hole, there is a question waiting that the sum over histories alone cannot answer. You are about to see how large that question actually is. Let us scale up now. Not gradually, violently. You have been standing in the territory of the very small. In the subatomic world where Feynman's path, integral, was born, where electrons drift through probability clouds and photons carry the weight of every path not taken. But the universe does not stop at the quantum scale. The universe is also vast, incomprehensibly, almost offensively vast. And the same principles that govern the behavior of a single electron in a laboratory at Princeton also governed the behavior of the first particles that existed in the first fraction of the first second after the Big Bang, when the entire observable universe was compressed into a volume smaller than a proton, and every structure you see in the night sky was still latent, still unformed, still nothing but a field of quantum fluctuations waiting to become something. This is where the scale of Feynman's insight truly begins to reveal itself. The observable universe contains, by current estimates, somewhere between 1 and 2 trillion galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. Each of those stars is a nuclear furnace sustained by quantum mechanical processes. By the tunneling of protons through energy barriers they classically should not be able to cross, but which they cross anyway, because in quantum mechanics, a particle can exist, with non-zero probability, on the other side of a barrier even without the energy to surmount it. This is quantum tunneling. Without it, the sun would not burn. Without it, no star would ever have ignited. The warmth you feel on your face on a clear day is quantum mechanics made macroscopic, made planetary, made survivable. But the story goes deeper than stellar fusion. In the first moments after the Big Bang, in the epoch physicists call inflation, when the universe expanded faster than light across a span of time, so brief it makes any human timescale look geological by comparison, quantum fluctuations in the density of the primordial field were stretched to cosmic scales. Tiny, random variations in the distribution of energy, fluctuations that existed because quantum mechanics forbids perfect uniformity at the smallest scales, were magnified by the expansion of space itself into density variations that seeded the formation of the first galaxies. The cosmic web, the vast filamentary structure of galaxy clusters and superclusters that spans the observable universe, the largest coherent structure known to exist, originated in quantum noise, in the irreducible, unavoidable uncertainty that Heisenberg described and Feynman formalized. Look at an image of the large-scale structure of the universe. The filaments of light connecting galaxy clusters across hundreds of millions of light years. The vast empty voids between them, dark and cold and nearly structureless. That entire architecture, That web that makes the universe look, from far enough away, like a neural network or a foam of bubbles, is a quantum mechanical fingerprint. It is what you get when you run a sum over histories at the scale of the entire cosmos, when you let the interference of possibilities operate not across a laboratory bench, but across the full extent of space and time, and then wait 14 billion years to see what settles out. The universe is not a classical machine that started running at the Big Bang and has been grinding forward mechanically ever since. It is a quantum system of almost incomprehensible complexity, whose present state is the residue of an interference calculation that began before time, as we understand it, even had a definite meaning. And the framework Feynman built, the sum over histories, is not merely a tool for understanding particles in accelerators. It is, when extended properly, a framework for understanding the history of the cosmos itself. Stephen Hawking and James Hartley understood this. In the early 1980s, they applied Feynman's path integral not to a particle moving through space, but to the universe itself, moving through the space of all possible geometries. In the Hartle-Hawking no-boundary proposal, the universe has no initial boundary in time, no moment at which it began in the classical sense. Instead, the birth of the universe is described as a sum over all possible compact, smooth, four-dimensional geometries, weighted by their probability amplitudes, from which the expanding space-time we inhabit emerges as the most probable outcome. The Big Bang, in this picture, is not a singularity at which time started. It is a point at which the time dimension becomes indistinguishable from space, where the distinction between before and after dissolves into a smooth, boundaryless surface, the way the surface of a sphere has no edge. This is Feynman's sum over histories extended to the universe as a whole. The cosmos, in this framework, has no unique history. It has a superposition of histories, and what we call the history of the universe, the sequence of events from the Big Bang to the present moment, is the most probable branch of that superposition, the path that dominates the interference pattern when all alternatives are summed. Let that reverberate for a moment. The universe you are sitting in right now, the specific sequence of events that led to the formation of the Milky Way, to the ignition of the sun, to the assembly of the earth, to the emergence of life, to the evolution of a species capable of asking these questions, is the peak of a probability distribution. It is the outcome that dominated the interference pattern of all possible cosmic histories. And surrounding it, in a mathematical sense that is not metaphorical, are the infinite other histories that contributed to the calculation and then vanished into destructive interference. Universes that collapsed back on themselves, universes that expanded so fast that no structure ever formed, universes whose physical constants were slightly different and whose stars never lit, never exploded, never scattered the heavy elements that become planets and oceans and the carbon chains that fold themselves into life. You exist at the crest of an infinite wave, and you would not exist if the wave had been slightly different, if the interference pattern had produced a different dominant history, if the quantum fluctuations in the inflationary field had been distributed differently, if the amplitude of a single term in the cosmic sum had shifted even a tiny amount. The specificity of your existence, the fact that you are here, made of the particular atoms you are made of, in a universe with the particular laws it has, is not a background fact about reality. It is a foreground mystery. But there is something even more disquieting waiting at the edge of this picture. Because the sum over histories, when applied to the cosmos, raises a question that Feynman's original formulation for particles was able to sidestep. A question about the observer, about what counts as a measurement, about who or what is doing the summing. When you measure a particle in a laboratory, you are outside the system. You are the observer, and the particle is the observed. The act of measurement collapses the quantum superposition into a definite outcome. But when the system under consideration is the entire universe, when the sum over histories includes you and your measuring apparatus, and the laboratory, and the planet, and the stars, and everything, there is no outside. There is no external observer to perform the measurement. There is no vantage point from which the cosmic wave function can be collapsed. This is not a technical problem waiting for a clever experimental workaround. This is a conceptual abyss. This is the place where Feynman's formalism, extended to its logical conclusion, arrives at a silence that physics has not yet learned to speak into. And at the center of that silence, dense, dark, and infinitely patient, there is a structure that embodies, in the most extreme physical form imaginable, every tension between quantum mechanics and the rest of what we know about the universe. You are about to approach a black hole. There is a place in the universe where physics stops working, not in the way that a machine stops working when it breaks, messily, visibly, with components scattered and functions clearly interrupted. It stops working the way a sentence stops making sense when a word in the middle has been quietly replaced with something that has no meaning in that language. From a distance, the structure looks intact. The equations stand. The symbols are all there. But when you follow the logic to its end, you arrive at a number that is not a number, a quantity that the mathematics refuses to assign a finite value, a point where the variables that describe space and density and curvature reach infinity, and infinity in physics is almost never an answer. Infinity in physics is almost always a sign that the theory has been asked a question it was never designed to answer. That place is the singularity at the center of a black hole. And the paradox it creates, the reason it has consumed decades of work from the most brilliant physicists alive, the reason Feynman's sum over histories is being drafted as part of the rescue effort, is not merely technical, it is foundational. It concerns what the universe is permitted to do with information. And if that sounds abstract, understand what information means in this context. It means history. It means the record of what has happened. It means the chain of causes and effects that connects the past to the present, the thread that allows the universe to be, in principle, comprehensible. A black hole is, first, a gravitational collapse. When a star massive enough, roughly 20 times the mass of the Sun or more, exhausts its nuclear fuel, the outward pressure that has been balancing gravity for millions or billions of years suddenly vanishes. Gravity wins. The core collapses inward at a fraction of the speed of light. The outer layers of the star are hurled outward in a supernova explosion visible across the entire observable galaxy. And what remains at the center continues collapsing, past the density of a neutron star, past any known state of matter, until it reaches a point, or what the equations call a point, of infinite density, a singularity. Around that singularity, at a distance determined by its mass, space itself curves so severely that the escape velocity, the speed you would need to travel to escape the gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. Not matter, not radiation, not information of any kind transmitted by any physical means. This boundary is the event horizon. Cross it, and the universe outside becomes permanently inaccessible. You are inside, you are falling. And falling, in the geometry of a black hole, means falling toward the singularity. Not because there is a force pushing you inward, but because the future, in that region of space, points only in that direction. The The singularity is not a place you fall toward. It is a time you fall toward. It is where your future ends. This is general relativity's description of a black hole. It is extraordinarily precise. The mathematics is internally consistent, observationally confirmed, breathtaking in its elegance. The image captured in 2019 by the Event Horizon Telescope, the first direct photograph of the shadow of a black hole, the supermassive object at the center of galaxy M87, a monster containing 6.5 billion solar masses, matched the predictions of general relativity with stunning fidelity. The theory works. It works so well that it seems almost indecent to ask what it might be missing. But it is missing something. Something enormous. In 1974, Stephen Hawking did something that no one expected. He applied quantum field theory to the region just outside the event horizon of a black hole and discovered that black holes are not perfectly black. They radiate. Not because anything escapes from inside the event horizon, nothing does, but because the quantum fluctuations of the vacuum, the constant spontaneous creation and annihilation of particle-antiparticle pairs that quantum mechanics requires even in empty space, are affected by the extreme curvature of space-time near the horizon. Occasionally, a pair forms just outside the horizon, and one particle falls in while the other escapes. The escaping particle carries energy. The black hole, by the law of conservation of energy, loses mass. It evaporates, slowly, unimaginably slowly for large black holes. A stellar mass black hole would take longer than the current age of the universe raised to a power that strains even the imagination to fully articulate. But eventually, completely. A black hole radiates, cools, shrinks, and disappears. And when it is gone, when the last quantum of Hawking radiation has been emitted and the event horizon has closed to nothing, what has happened to everything that ever fell in? The matter that collapsed to form the black hole, the stars, the planets, the gas clouds, the astronauts and civilizations, if any such things fell in. The photons and particles that crossed the horizon over the course of the black hole's life. All of that carried information. The specific quantum states that described each particle, each atom, each configuration of matter and energy. That information cannot simply disappear. Quantum mechanics, at its most fundamental level, is based on the principle that information is conserved. The laws of quantum mechanics are unitary. The evolution of a quantum system is always reversible in principle. Information is never truly destroyed. But if a black hole forms, consumes information, and then evaporates into Hawking radiation that carries no record of what fell in, then information has been destroyed. The universe's history has been erased. The chain of causality that connects past to present has been severed. This is not a technical inconvenience. This is a violation of one of the deepest principles in physics. This is the black hole information paradox. And it is here, in this specific, precisely defined conflict between general relativity and quantum mechanics, that Feynman's framework reappears with new urgency. Because the sum over histories, the path integral, is a quantum mechanical tool. It works in the language of quantum mechanics. And if the information paradox is to be resolved, if the laws of quantum mechanics are to survive their confrontation with the most extreme gravitational objects in the universe, then it will require a formalism capable of describing the geometry of space-time the way Feynman described the path of a particle. As a superposition, as a sum, as a wave of possibilities whose interference determines what is real. This is the frontier. This is what physicists like Juan Maldacena, Leonard Susskind, and many others are working on now. The attempt to extend the sum over histories to the geometry of space-time itself. to describe black holes and their interiors as quantum systems whose information is preserved in the radiation they emit, encoded not in any single emission, but in the vast, almost incomprehensible correlations between emitted particles across the entire evaporation lifetime. The answer, if it exists, requires physics that has not yet been fully written. It requires a quantum theory of gravity, a framework that does for space-time what Feynman did for the electron. And every serious attempt to build that framework has produced, as a byproduct, a picture of reality that is stranger, richer, and more disorienting than the picture it replaces. The singularity at the center of a black hole is where general relativity breaks down. But the information paradox is where quantum mechanics is being tested in a way it has never been tested before. Against gravity, against the structure of space-time itself, against the question of whether the universe's memory is indestructible or merely persistent. And somewhere in that confrontation, in the mathematical space between what we know and what we cannot yet say, the deepest question of all is taking shape. Not a question about black holes, not a question about particles, a question about the nature of space and time themselves, about whether they are fundamental features of reality or whether they are, like the solidity of a rock, an emergent approximation that dissolves when you look closely enough. You are about to look closely enough. Space feels like a container. That is probably the most natural assumption a human being can make about the universe. That space is the place where things happen. The vast, empty vessel in which matter and energy move and interact and accumulate into structures. Space is the stage. Gravity, electromagnetism, the nuclear forces, these are the actors. And time is the director, moving everything forward in a single, fixed direction, from past to present to future, without deviation, without exception. This picture is wrong. Not approximately wrong. Not wrong at the edges while remaining useful at the center. Wrong in a way that reaches into its foundations, into the very definition of what space and time are, and replaces the stage and actor's metaphor with something that has no clean analogy in human experience. Einstein showed us the first level of wrongness in 1915, with general relativity. Space is not a passive container. It is a dynamic field, a geometry that bends and warps in the presence of mass and energy, and whose bending is what we experience as gravity. The Earth does not orbit the Sun because there is a force pulling it inward across empty space. The Earth follows a straight line through curved space-time, the most natural, unaccelerated path available to it, which happens to be an ellipse when projected onto our familiar three-dimensional picture of the solar system. Gravity is not a force. It is geometry. It is the shape of the universe. This was already a radical departure from intuition, but general relativity left space-time as something continuous, smooth, and infinitely divisible, a fabric that could be curved to any degree, but that did not have a texture at the smallest scales, a fabric without threads. Quantum mechanics suggested otherwise. The Planck length, named after Max Planck, who first identified it in 1899 from dimensional analysis alone, before quantum mechanics as a theory even existed, is approximately 1.6 times 10 to the power of negative 35 meters. To call it small is to commit a spectacular failure of language. A proton is 20 powers of 10 larger than the Planck length. If you scaled a single proton up to the size of the observable universe, the Planck length would become, in that expanded scale, roughly the size of a proton. This is the scale at which, if current theoretical physics is anywhere near correct, space-time itself ceases to be smooth. At the Planck scale, the quantum fluctuations of the gravitational field, the quantum uncertainty in the very shape of space, become of order 1. The geometry of space-time is no longer a well-defined classical entity. It fluctuates. It foams. It is, in some frameworks, no longer meaningfully a geometry at all. John Wheeler called this space-time foam. The image is vivid and deliberately unsettling. At the smallest scales, space is not flat or smoothly curved. It is violently turbulent, constantly fluctuating between different topological configurations, sprouting and annihilating tiny wormholes and curvature spikes on timescales of the Planck time, approximately 5 × 10 to the power of -44 seconds, the briefest interval that current physics assigns any physical meaning to. You cannot see this. No instrument built or imaginable can probe these scales directly. The energy required to resolve a feature at the Planck length is, by the uncertainty principle, equivalent to the mass energy of a microscopic black hole, which would instantly evaporate in a burst of Hawking radiation. The Planck scale is, in a precise technical sense, the smallest thing the universe will allow you to look at. Below it, the concept of looking may not apply. The concept of below it may not apply. This is where Feynman's sum over histories becomes something more than a computational tool. When physicists working on quantum gravity attempt to apply the path integral to the geometry of space-time, when they try to write down a sum over all possible space-time geometries the way Feynman wrote a sum over all possible paths for a particle, they are asking what the universe looks like when space and time themselves are subject to quantum superposition, when the stage is not fixed, when the director has no fixed clock, when the geometry of reality is itself a fluctuating quantum field that must be summed over, weighted, interfered with, and read off as a probability distribution. The difficulty of this project cannot be overstated. For a particle, the sum over histories is difficult but tractable. The space of possible paths is vast but mathematically manageable. For the geometry of space-time, the space of possible geometries is not just vast, it is, in mathematical terms, intractable in ways that have resisted decades of effort by thousands of physicists. The path integral over geometries diverges in ways that are deeply different from the divergences Feynman encountered in QED, which he and others learned to manage through a technique called renormalization. Gravity, unlike electromagnetism, is not renormalizable by the same methods. Every time you try to remove the infinities from the quantum theory of gravity, using standard techniques, new infinities appear, requiring new parameters, which generate new infinities, without end. The theory is sick. It cannot be fixed by the tools that fixed every other quantum field theory. This failure is not a minor technical setback. It is the central unresolved problem in fundamental physics. It has been unresolved for nearly a century. The greatest minds of the 20th and 21st centuries have worked on it. Einstein himself spent the last 30 years of his life trying to unify gravity with electromagnetism, without success. String theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety. Each of these approaches represents a different strategy for taming the quantum behavior of spacetime, for making the sum over geometries well-defined and finite, for writing down a theory that reduces to general relativity at large scales and to quantum mechanics at small scales, and is consistent and predictive at all scales in between. None of them is finished. None of them has produced a prediction, distinct from what existing theories already predict, that has been confirmed by experiment. The problem is not lack of intelligence or effort. It is that the Planck scale is simply inaccessible to direct experimental probing by any technology conceivable within physics, as we currently understand it. We are building theories about the foundations of reality in a regime we may never directly observe. And yet, the clues exist. They come from places where gravity and quantum mechanics are both important, but not yet lethally incompatible. From the early universe, from the edges of black holes, from the mathematical structure of the theories themselves. And one of the most important clues came not from an experiment, but from a calculation performed in 1997 by a young Argentinian physicist named Juan Maldacena, working at Harvard, who discovered something that seemed almost too beautiful and too strange to be true. Maldacena showed that a quantum theory of gravity in a certain curved space-time, a five-dimensional anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on the four-dimensional boundary of that space. The bulk and the boundary. Gravity in 5 dimensions and no gravity in 4. Two completely different-looking theories describing completely different-looking physical setups containing exactly the same information, related by a precise mathematical dictionary that allows you to translate any statement in one language into a statement in the other. This is the ADS-CFT correspondence. And what it implies, if it is correct, and if it generalizes beyond its specific setting, is something that strikes at the heart of everything you thought you knew about space. Gravity, and perhaps space-time itself, may be emergent. It may not be fundamental. It may arise the way temperature arises from the average motion of molecules, from something more basic, from the entanglement structure of a quantum system that does not, itself, live in space-time at all. Space as an emergent phenomenon. Time as an emergent phenomenon. The geometry of the universe as a holographic projection from a lower dimensional boundary, the way a flat hologram encodes a three-dimensional image without itself being three-dimensional. If this is right, and there is growing evidence, mostly theoretical but internally compelling, that it is at least pointing in a true direction, then Feynman's sum over histories, when extended to the geometry of space-time, is not just a sum over paths in space. It is a sum over the configurations of a quantum system from which space itself emerges. The universe is not a container. The universe is not even a stage. The universe is, perhaps, the interference pattern produced by a quantum computation running on a substrate that is not made of space or time, but of something more primitive. Something we do not yet have a name for. The ground has not just given way. It was never there to begin with. Every answer in this territory opens a larger question. That is not a rhetorical device. It is a structural feature of the frontier of physics, and it has been true for as long as there has been a frontier. When Newton unified the motion of planets and falling apples into a single law of gravitation, the answer was extraordinary. But the question it opened was immediate and haunting. What is gravity, actually? What is the mechanism? How does the sun reach across 93 million miles of empty space and pull on the Earth without touching it? Newton himself refused to speculate. He called it action at a distance and moved on. The mechanism remained mysterious for 2 centuries until Einstein replaced it with geometry. And geometry, when pushed to its limits, opened the singularity problem. And the singularity problem opened the information paradox. And the information paradox opened the possibility that space-time is emergent. An emergent space-time opens a question so fundamental that it may be the deepest question physics has ever been forced to ask. What is entanglement? Not in the sense of how it behaves. That has been known since the 1930s, and the experimental tests of Bell's inequalities in the 1970s and 1980s confirmed it beyond any reasonable doubt. Entanglement is real. 2 particles can be prepared in a shared quantum state, such that measuring one instantly determines the outcome of measuring the other, no matter how far apart they are. Not because a signal traveled between them, not because one influenced the other, but because they share a single quantum state that cannot be factored into 2 independent descriptions. They are, in a precise mathematical sense, one system, even when separated by any distance, even when separated by light years. Einstein called it spooky action at a distance. He hated it. He spent years trying to show it was a symptom of incomplete theory, that there were hidden variables underlying quantum mechanics that would restore local realism and banish the spookiness. The Bell inequalities ruled that out. There are no hidden variables. The entanglement is real. The non-locality is a genuine feature of the quantum world, and accepting it changes everything about what you think a quantum system is. A quantum system is not a collection of particles with properties. It is a web of correlations, entanglement relationships between degrees of freedom, from which what we call particles and properties emerge, approximately, in certain regimes. The particle picture, like the classical picture, is an approximation. It is what the entanglement web looks like from far away, at low resolution, in the limit where quantum coherence is suppressed by decoherence, and classical behavior emerges from the underlying quantum substrate. Now bring this back to spacetime. In 2013, Maldacena and Leonard Susskind published a short but electrifying paper proposing a specific relationship between entanglement and geometry. Their paper concerned a configuration that has fascinated physicists since Einstein and Rosen first described it in 1935. The wormhole, or Einstein-Rosen bridge, a theoretical tunnel through spacetime connecting two distant regions, or even two separate universes. In the ADS-CFT framework, Maldacena and Susskind argued that two entangled black holes are connected by a wormhole. The entanglement between the two black holes, the quantum correlation between their states, is what creates the geometric connection between them. The wormhole is not a separate structure added on top of the entanglement. The wormhole is the entanglement, described in the language of geometry. Their paper carried the elegant shorthand, ER-EPR. The Einstein-Rosen bridge equals the Einstein-Podolsky-Rosen entanglement. Geometry equals entanglement. Space is woven from quantum correlations. The implications cascade outward with a kind of vertiginous acceleration. If entanglement generates space-time geometry, if the geometric distance between two regions of space is related to the degree to which the quantum degrees of freedom in those regions are entangled, then the fabric of space is not a pre-existing structure. It is a relational structure. It is built, moment by moment, from the entanglement relationships between the quantum constituents of reality. Regions that are highly entangled are geometrically close. Regions that are disentangled are geometrically far apart. And if you could somehow reduce the entanglement between two regions to zero, the geometry connecting them would not just stretch, it would tear. Space-time would develop a discontinuity. The smoothness that general relativity assumes at all points would fail, locally and physically, as a consequence of a quantum mechanical operation. This has been called entanglement entropy, as the source of space-time. Shinsei Ryu and Tadashi Takayanagi formalized it in 2006, deriving a precise formula relating the area of a minimal surface in the bulk spacetime to the entanglement entropy of a region on the boundary. A formula that has since become one of the most cited results in the overlap between quantum information theory and quantum gravity. The area of a geometric surface, measured in Planck units, equals the entanglement entropy of the corresponding boundary region. Geometry, measured in meters squared, equals information, measured in bits. Geometry is information. Space is a property of entanglement. Distance is a measure of correlation. And here, precisely here, the full weight of what Feynman started begins to press down. Because the sum over histories, applied to the geometry of space-time, cast in the language of entanglement, interpreted through the ADS-CFT dictionary, becomes a sum over all possible entanglement configurations of the boundary theory. The path integral over geometries becomes a partition function over quantum informational states. The birth of the universe described by the Hartley-Hawking wave function, becomes a quantum computational process, an initialization of the entanglement structure from which space-time crystallizes. You began this journey with a particle taking every possible path between 2 points. You are now standing at the edge of a framework in which the universe itself, every galaxy, every star, every atom, the full sweep of cosmic history, is a particular entanglement pattern in a quantum system whose underlying description contains no space, no time, no geometry. Those things emerge. They are derived. They are the macroscopic, large-scale approximation of a reality that is, at its foundation, purely quantum informational. But here is where the complications do not resolve. They multiply. If space-time emerges from entanglement, then what happens to space-time when entanglement is disrupted? The black hole information paradox becomes, in this light, not a problem about information falling into a gravitational well. It becomes a problem about what happens to the space-time geometry when the entanglement structure it was built from is modified by the evaporation of the black hole. Hawking radiation, in this picture, is the process by which the black hole slowly transfers its entanglement with the interior to entanglement with the radiation field outside. The geometry of the interior changes as the entanglement structure changes, and at late times, as the black hole approaches the end of its evaporation, the geometry of the interior may become, in a meaningful physical sense, the geometry of the radiation field itself. This is the firewall paradox, proposed by Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully in 2012. It suggests that the smooth, uneventful event horizon that classical general relativity predicts, the gentle threshold you could cross without noticing in a sufficiently large black hole, may not be smooth and uneventful at all. It may be a wall of high-energy radiation, a firewall, created by the modification of the entanglement structure as the black hole ages. The equivalence principle, the foundational principle of general relativity, the statement that you cannot locally distinguish between gravity and acceleration, may be violated at the horizon of an old black hole. General relativity says the horizon is smooth. Quantum mechanics says it may not be. They cannot both be right. Every resolution proposed so far requires discarding something that was thought to be fundamental. Smooth horizons, locality, unitarity, the equivalence principle. At least one of them must give way. The physics does not yet know which. The mathematics does not yet know how. Feynman, who built the first tool powerful enough to reach this place, spent his career insisting that the job of a physicist is not to make nature conform to human comfort. Nature does not care what makes sense to you. It does what it does, and what it does, in the territory where gravity and quantum mechanics collide, is something that neither of the two greatest theories ever constructed is equipped to fully describe. The question is now larger than any single theory. The question is now about the nature of nature itself. And it is about to get personal. You are made of approximately 7 billion atoms. That number, 7 followed by 27 zeros, is not presented here for shock value. It is presented because it is the scale at which the questions we have been asking become intimate. Because each of those atoms is a quantum system. Each of its electrons exists in a superposition of states until it interacts with something. Each of its nuclear constituents is governed by the same quantum chromodynamics that governs quarks in particle accelerators. The Feynman path integral is not a description of abstract particles in theoretical laboratories. It is a description of the actual physical substrate of your body, operating right now, at this moment, in the space between your reading of one word and the next. You are not an observer of the quantum world. You are a product of it. You are, in a rigorous and non-metaphorical sense, a macroscopic quantum system whose coherence has been suppressed by an almost incomprehensible amount of thermal noise and environmental decoherence, leaving you with the classical, deterministic-seeming behavior of a large, warm, wet object moving through a room-temperature world. But the suppression of coherence is not its elimination. It is its averaging. And what has been averaged, what has been smoothed and damped and rendered classical by the relentless bath of thermal interactions, was once, at the moment of your formation, at the moment of each atom's synthesis in the cores of stars long dead, a fully quantum process. The carbon in your body was forged in the triple alpha process inside red giant stars, a fusion reaction in which 3 helium nuclei combine to form a single carbon nucleus, mediated by a nuclear resonance whose existence was predicted by Fred Hoyle in 1953 and confirmed by experiment shortly after. Hoyle predicted it not from theory, but from anthropic reasoning. Carbon exists in the universe. Therefore, the nuclear physics of helium fusion must permit its formation. Therefore, there must be a resonance that makes the reaction probable enough to occur at stellar temperatures. He predicted a property of the carbon nucleus from the fact that he himself was made of carbon. The nuclear resonance exists. The carbon is here. You are here. And the quantum mechanical process that produced that carbon. The tunneling of helium nuclei through nuclear potential barriers. The resonant coupling of quantum states that allows the reaction to proceed at the temperatures inside a stellar core was a specific instance of the sum over histories operating at nuclear scales. The triple alpha process happens because the relevant quantum states interfere constructively, because the probability amplitudes for the reaction add coherently, because, in Feynman's language, the paths that lead to carbon reinforce each other, and the paths that lead to other outcomes largely cancel. You are the constructive interference of a nuclear reaction in a star. Let that be stated again, plainly. The atoms in your body were assembled by quantum mechanical interference in stellar cores, the same mathematical structure that describes a single electron in a double-slit experiment describes the process that built the chemical elements, that built the molecules, that built the cells, that built you. The sum over histories is not a description of physics that is separate from biology, from chemistry, from the story of life. It is the foundation beneath all of those stories. It is the layer of reality from which every other layer, including the layer you call yourself, emerges. This is not a poetic statement. It is a physical one, and it carries consequences that extend into the future with the same vertiginous force with which it reaches into the past. Quantum computing is perhaps the most direct technological expression of this understanding. A classical computer operates on bits, units of information that are either 0 or 1, either on or off at every moment. A quantum computer operates on qubits, quantum mechanical systems that can exist in superpositions of 0 and 1 simultaneously, and that can be entangled with each other such that their states are correlated in ways that have no classical analog. A quantum computer with 300 entangled qubits exists in a superposition of 2 to the power of 300 states simultaneously, more states than there are atoms in the observable universe, and can, in principle, perform computations on all of those states at once, with the answer emerging like the result of a path integral from the interference between all those parallel computations. This is not science fiction. Quantum computers exist. They are small, noisy, difficult to operate, prone to decoherence, and far from the general-purpose machines that will one day transform computation. But they work. The interference is real. The superposition is real. And the companies and governments and research institutions investing billions of dollars in their development are investing not in a metaphor, but in the direct technological exploitation of the same quantum mechanical principle that Feynman formalized. The principle that reality, at its computational foundation, processes all possibilities simultaneously and produces answers from their interference. A sufficiently powerful quantum computer could simulate quantum field theories that are intractable on classical hardware. It could model the behavior of molecules with quantum chemical accuracy, enabling the design of drugs and materials and catalysts that classical computation cannot predict. It could, in principle, simulate the early universe, reproduce in a controlled quantum system the quantum fluctuations of the inflationary field that seeded every galaxy that exists. It could bring the sum over histories from the level of theoretical framework to the level of laboratory tool, allowing us to ask questions about quantum gravity in a controlled setting for the first time. This is the near future. Not certain. The engineering challenges are enormous and may take generations to overcome, but physically possible in a way that, a century ago, would have required you to discard almost everything you thought you knew about what computers were. But the quantum implications do not stop at technology. They press inward into consciousness, into the question of what it means to be an observer in a universe described by a wave function that includes everything, including you. The measurement problem. The question of what causes quantum superpositions to collapse into definite outcomes and what counts as a measurement remains the most philosophically contested issue in all of physics. The Copenhagen interpretation, which dominated physics for most of the 20th century, essentially said, "Do not ask." The wave function is a tool for calculating probabilities. When a measurement is made, it collapses. What causes the collapse is not a question physics can answer. Accept the predictions and do not demand a mechanism. Feynman was largely, pragmatically, in this camp. Calculate, predict, measure. Agree with experiment. The rest is philosophy. But the many worlds interpretation, proposed by Hugh Everett in 1957 and championed by physicists like David Deutsch and Sean Carroll, takes the path integral at its word in a way that is almost nauseating in its implications. In many worlds, the wave function never collapses. Every time a quantum measurement is made, every time a superposition interacts with a measuring device, with an environment, with anything, all outcomes occur. The universe branches. Every possible result of every quantum interaction has always happened in a branch of the universal wave function that is real but no longer accessible to you, because decoherence has made the branches mutually invisible. The universe is not one history. It is all histories, running in parallel, each as real as the one you inhabit. You, in this picture, are not a single observer navigating a single timeline. You are a branch of a wave function, one outcome in an infinite proliferation of outcomes. And the you that exists here, reading these words in this branch, is accompanied by an uncountable multiplicity of versions of you who made every quantum-level different choice, who live in worlds where every quantum coin flip landed differently, where the constructive interferences that built your carbon atoms happened with slightly different amplitudes, where the stars that forged the atoms that became your body lived and died on slightly different timescales. Whether many worlds is correct is not settled. It may not be a question that is experimentally settleable in principle, but it is the most literal reading of the mathematics, the interpretation that takes the Schrödinger equation seriously at all scales, that applies the sum over histories without restriction, that refuses to insert a collapse, postulate not present in the original formalism. And if it is correct, then what Feynman gave us is not just a calculation tool. It is a map of everything that exists, a description of a reality so vast and so strange that the universe you can observe is an infinitesimally thin slice of it, a single branch in a tree whose full extent is, and may forever remain, beyond any possible observation. The consequences of that, for identity, for meaning, for the concept of a self navigating a single continuous history, are not small. They press on the question of who you are in a way that no previous scientific discovery has quite managed to press. Every rock thrown, every photon emitted by every star, every quantum event in every atom of every brain that has ever thought a thought, all of it branching, proliferating, expanding outward into a space of possibilities so immense that calling it infinite does not quite capture the weight of it. And the question that waits at the end of all this, the question that the sum over histories, followed to its ultimate conclusion, deposits you in front of, is not a question about particles or black holes or the structure of space-time. It is a question about what it means to exist at all. There is a certain kind of silence that descends when you have followed a question far enough. Not the silence of emptiness, not the silence of having run out of things to say. The silence that descends when language, which was built for a world of medium-sized objects and medium-paced events, arrives at the boundary of what it was designed to cross, and stops, not because the territory ends, but because the map does. You are standing at that boundary now. You have followed the sum over histories from a particle in a laboratory to the birth of the cosmos. You have watched space-time dissolve into entanglement, and entanglement dissolve into quantum information, and quantum information gesture toward something beneath it that has no name yet. And now you are standing at the edge of the map, looking out at the territory beyond, and the honest thing, the only honest thing, is to acknowledge what you are seeing. You are seeing the limits of human thought as it currently exists. That statement is not defeatism. It is not an invitation to mysticism. It is a precise and empirically grounded observation about the state of knowledge at this moment in history. Physics has, in the course of a single century, dismantled the classical picture of a deterministic, locally real, continuous universe and replaced it with a quantum mechanical picture whose implications are still being traced, whose interpretations are still contested, and whose unification with gravity, after 100 years of effort by the most brilliant scientific minds our civilization has produced, remains incomplete. We do not yet have the final theory. We do not yet know the deepest rules. We are, in the words Feynman used to describe this condition, lost in the forest. But we can see the light through the trees. What Feynman gave us with the path integral is one of the most powerful lights we have. Consider what it means, truly, to sum over histories. To say that a particle does not take a path, but takes all paths, and that the one path you observe is the constructive residue of their mutual interference. This is not a statement about ignorance. It is not saying that the particle really took one specific path, and you do not know which one. It is saying something ontologically more radical, that the concept of a single definite path is not applicable to the particle at all. Until the moment of observation, the path is not hidden. The path does not exist. What exists before the observation is the superposition, the totality of possibilities, weighted and interfering, waiting to collapse into actuality at the moment of interaction. Now expand that principle to the universe, not metaphorically, physically. The Hartle-Hawking wave function describes a universe that has no definite history until the history is in some sense observed, measured, recorded, interacted with. The universe's past is not fully determined in advance. It is, in a technical sense, that some physicists accept and others dispute, partly fixed by the present, by what exists now that could interact with and thereby actualize the past. The arrow of time, the apparent fixity of the past, the sense that history is a single determined sequence of events leading inexorably to this moment. These may not be fundamental features of the universe. They may be emergent properties of large, highly entangled quantum systems that have undergone enough decoherence to lose their quantum coherence and behave at the scales accessible to us, like classical machines moving through a single deterministic history. The past is not as fixed as it feels. This is the vertigo that physics offers now, not the vertigo of size or distance, though those are real enough, but the vertigo of ontological instability. The vertigo of realizing that the categories you use to navigate the world, object, position, path, cause, before, after, here, there, are not written into the bedrock of reality. They are human scale approximations, useful and reliable at the scales your nervous system evolved to navigate, but inapplicable at the scales where the actual mechanisms of the universe operate. The bedrock is quantum. The bedrock sums over histories. The bedrock does not care about your categories. And this, perhaps, is the most important thing Feynman actually taught. Not a formula, not a technique, not even a physical principle, but an epistemic posture, a way of standing in relation to the unknown. He called it the pleasure of finding things out, but it was more than pleasure. It was a refusal to be comforted by false understanding, a refusal to accept an answer that merely restates the question in more technical language, a refusal to pretend that naming something is the same as explaining it, that familiarity is the same as comprehension. Feynman was, above all else, honest about what he did not understand. And that honesty was not a weakness. It was the engine of everything he discovered. We do not understand what observation is at the quantum level. We do not understand why there is a single classical history at all, given that the underlying physics describes a superposition of all histories. We do not understand how space-time emerges from entanglement. We do not understand what happens at the singularity. We do not understand whether many worlds is true, or whether the wave function collapse is physical, or whether the universe has a wave function in the sense that a particle has a wave function. We do not understand what came before the Big Bang, if the question even has meaning. We do not understand why the fundamental constants of physics have the values they have, the values that permit atoms, stars, planets, oceans, biology, and consciousness to exist. We do not understand whether consciousness has any role in the physics of observation, or whether it is simply one more physical process, subject to the same quantum mechanical rules as everything else, producing the illusion of a privileged observer through the same emergent classical behavior that makes rocks feel solid. These are not small gaps in an otherwise complete picture. They are not the last remaining patches of darkness in a mostly illuminated map. They are the central questions, the questions from which all other questions about the nature of reality flow. And they are open, genuinely, irreducibly open. Not because we have not yet done the right experiment, but because the questions themselves are pointing at a level of reality whose description requires concepts we do not yet have. Here is what we do know. We know that the universe at its most fundamental level is quantum mechanical. We know that quantum mechanics is the most precisely confirmed physical theory in history. We know that the sum over histories, Feynman's extraordinary insight, born from the mind of a young man in Princeton who simply refused to stop asking why, is a correct description of the mechanism by which reality operates at the quantum scale. We know that this mechanism, when extended to the cosmos, describes the birth of the universe, the formation of structure, the behavior of light across billions of light years, the burning of stars, the synthesis of the atoms in your body. We know that it conflicts, at the most extreme scales, with general relativity, and that resolving that conflict is the task that will define the next era of physics. And we know, this is perhaps the most important thing we know, that every previous time physics has encountered a conflict between two apparently incompatible frameworks, the resolution has revealed a deeper layer of reality that was not visible from either framework alone. Newtonian mechanics and Maxwellian electromagnetism conflicted, and the resolution was special relativity. Newtonian gravity and special relativity conflicted, and the resolution was general relativity. Classical mechanics and experiment conflicted, and the resolution was quantum mechanics. Each resolution was not a compromise between the two frameworks, it was a transcendence, a new layer that contained both as limiting cases and revealed something neither had glimpsed. The conflict between quantum mechanics and general relativity is the deepest such conflict physics has ever faced. And the resolution, when it comes, if the century or millennium that produces it lies ahead of us rather than behind, will reveal a layer of reality that makes quantum mechanics look, in retrospect, like the first dim outline of a truth that was always much larger than we imagined. A truth in which space and time are not fundamental, in which the distinction between observer and observed dissolves, in which the question of what is real and what is merely possible is answered in a way that neither word, as we currently use them, adequately captures. You began this journey standing in front of a rock that felt solid. You end it standing in front of a universe that is, at every scale and in every direction, stranger and richer and more profound than the solidity of that rock could ever have suggested. The rock is still there. It is still real in all the ways that matter to your daily life. But beneath it, beneath the molecules, beneath the atoms, beneath the quarks, beneath the foam of space-time at the Planck scale, in the substrate from which space and time and matter and energy all emerge, there is something that does not have a name yet, something that the sum over histories is pointing toward, the way a shadow points toward an object that is still just outside your field of view. Feynman once said that the universe is not obligated to make sense to you, but he spent his entire life listening to it anyway, with precision instruments and mathematical formalisms and an unrelenting appetite for reality as it actually is, rather than as it would be convenient for it to be. And what he heard, when he listened carefully enough, was not comfort. It was something better than comfort. It was the sound of a universe that is infinite in its strangeness, inexhaustible in its depth, and, perhaps this is the most human thing that can be said about it, generous enough to let us hear it at all. You are a sum over histories, a superposition of every possible version of you that quantum mechanics permits, collapsed, by every interaction, every measurement, every moment of consciousness pressing against the world, into this specific, improbable, temporary, luminous instance of existence. You are what happened when the wave functions of the atoms in a long-dead star interfered constructively enough to eventually produce something that could ask what it is made of. And the answer, the real answer, the one that physics is still assembling from Feynman's path integral outward, is that you are made of the same thing the universe is made of. Not the same matter, the same process. You are the universe asking itself, through the only instrument it has ever built that was capable of the question, what it means to exist. That question has no final answer. It only has deeper ones, and the depth, it turns out, is bottomless.